everybody, Mrs. Pesic here. We are watching a video on section 2.1. Chapter 2 is about polynomials and rational functions, and section 2.1 is about quadratic functions and models. So let's take a look at some examples of polynomial functions. You could have a polynomial function like 5x squared minus 3, or you could have a polynomial function like 7x to the 5th minus 3x squared plus 2x minus 6. Those are examples of polynomial functions. So in general, we can write a polynomial function of x with degree n as this: f of x equaling a times x to the n plus a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2. And we would keep this pattern going all the way down to a sub 1 x to the first and a sub 0 times x to the 0, but x to the 0 is just 1. So a sub 0 would be our constant term. So let's take a look at this, and what does this all mean? Well, the a sub n minus 1, the a sub n minus 2, and so on are all real numbers with a sub n not allowed to equal 0. That's this leading coefficient here. A sub n not allowed to equal 0 because we want to be able to say, hey, this is the highest power on any term, the n, and so we want to be able to say, hey, this is degree n. All right, so this is a degree n polynomial function. All right, and n is not allowed to be, and n is any non-negative integer. Okay, so we can classify polynomial functions by degree. So, for example, if you have f of x equaling, for example, just some kind of constant, like f of x equaling c, so an example of that might be f of x equaling 9. We would call that, just what I said, that's a constant function. All right. What if we had f of x equaling some number times x and maybe plus another number? Well, an example of that might be, f of x equaling 2x minus 1. Well, that would be an example of a linear function, degree 1. All right. So this is a degree 0. That's a constant function. This is a degree 1. That's a linear function. A degree 2 would look something like f of x equaling ax squared plus bx plus c. An example of that might be f of x equaling 3 halves x squared minus 5x plus 1. And that would be an example of a quadratic function. If we go up to a degree 3, that would be a cubic function. A degree 4 is a quartic function. But we're not going to be looking at those today because we really just want to focus on the quadratic function. All right? So in our example, let a, b, and c be real numbers. A is not allowed to equal 0. Then f of x equaling a x squared plus bx plus c is going to be a quadratic function. All right, remember you can pause this video at any time if you need to. Okay, so the graph of a quadratic function is always going to be a U-shaped parabola. And the parabola might open up like this, or it might open down like this, but it's going to be U-shaped. There's so many real-life examples of quadratic functions. The path of a golf ball. So if you're hitting a golf ball, the path that it makes in the air before it hits the ground is a parabola. If you've ever opened up a flashlight, the bulb, this is our flashlight, kind of the cross section of our flashlight here. There is a bulb that's lighting the way here, and there is a reflecting dish, if you will, a shiny thing that's going to force all of the light whenever it hits it to go bounce straight off it, and that's why you get a beam of light coming off the coming out of the flashlight. All right, so lots of examples of parabolas in real life. Okay, so the vertex is the point on the parabola where the axis intersects the parabola. So we didn't talk about the axis yet. So if we have a parabola, let's say the parabola is looking something like this, and the parabola is symmetric, right? There's a line of symmetry here. So I've got half the parabola on one side of the line, half the parabola on the other side of the line. This line here is called the axis of symmetry. Okay, and the vertex is going to be the point where the axis of symmetry intersects the parabola. So that would be right here. So this point right here is called the vertex. Okay, how do you know whether your parabola is going to be opening up or down? Well, if your leading coefficient is positive, it's going to open up. And if the leading coefficient is negative, it's going to open down. So again, this is our general form for a quadratic function. We set that right here. And our leading coefficient is going to be the A. That's the leading coefficient. So if A is greater than 0, then the parabola opens up. If A is less than 0, that parabola is going to open down. So the picture here would look something like this. Picture here would look something like this. Okay, so let's now look at comparing the graphs of y equals x squared and 1/2 x squared and y equals x squared and 3x squared. So if you graph this on your calculators, let's just take a quick look at these graphs. We're just going to do x squared. Here's our parent function. And we want to do 1/2 x squared. So let me push tab, and I'm going to do parentheses 1/2. Actually, I don't like that. Let's do this. Delete. Let's do control divided by, to pull up a fraction template. I want 1/2, and then I want x squared. So what's happening? My 1/2 x squared graph is looking wider. And we talked a lot about transformations, so I hope that you are recognizing that the 1/2 x squared has been vertically compressed by a factor of 1/2. Not horizontally smooshed or stretched or anything like that. It's been vertically compressed by a factor of 1/2. All right, what about x squared and 3x squared? Well, if I add 3x squared to the same one, 3x squared, and I look at that graph is much narrower, and that's because the 3x squared has been vertically stretched. So this one is an example of a vertical compression of 1/2, and this one is an example of a vertical stretch of 3. All right. Okay, so if you recall from our work with transformations, if you add a number or subtract a number to a function, what happens? Well, for example, if I have f of x equaling x squared as my parent function, how is the graph of, I'll call it g of x, how is the graph of g of x, if g of x is, let's say, x squared minus 2, how is that going to look different than the parent function? Or what about if I have h of x equaling x squared plus 3? How is that going to look? Well, I hope that you remember that this is going to be a vertical shift. This one's going to be down 2, and this one's going to be a shift up 3. And you can take a look at that on the calculator and verify that yourself. What about if we are adding or subtracting a number to the x itself? So how is that going to be different? So again, if I have a parent function, f of x equaling x squared, and so what is going to look different if I have g of x equaling x plus 2 quantity squared? Or g of x, or I'll say h of x equaling x minus 4 quantity squared. Well, let's investigate to make sure we're remembering how that works. So we are going to, let's see, I'm going to add a new page, graphs page. I'm going to clear this thing out of here. And so we're going to have our parent functions x squared. And let's say we push tab and we want to do parentheses, and what was my first one? X plus 2 quantity squared. So if I do x plus 2, close parentheses, hit the squared button, that graph has been shifted 2 units to the left. And what if we do x minus 4 quantity squared? I push the tab, and parentheses, x minus 4, close parentheses, squared. And that one has been shifted 4 units to the right. So hopefully you remember that from all of our work with transformations. So this is a shift left 2, and this one is a shift right 4. Okay, so for the equation y equals x minus 3 quantity squared plus 2, what transformations are going on? Well, I hope that you see that the transformation would be that you're going to shift right 3 and up 2. So 2 transformations going on. If we're shifting this parabola 3 units to the right and 2 units up, let's say the parent function was here, okay? If I'm shifting this graph 3 units to the right and 2 units up, then that vertex went from 0, 0 to what new point? Well, hopefully you're going to say, hey, it's right here at 3, 2. So that's our vertex for this one. Let's take a look at another example. What about this one? The transformations here, I'm hoping you're going to tell me that it's a shift left 5 and down 7. So again, where's the vertex going to be? If my parent function fx equaling x squared was looking like this, and I want to shift to the left 5 and down 7, well, my vertex is no longer at 0, 0. It's going to the left 5 and down 7. So that vertex is going to be at negative 5, negative 7. All right, let's take a look at another example. What if we have this function, f of x equaling negative 8x squared minus 7? We've got 3 different transformations going on here. So remember, if you've got a number being multiplied by your function, then that's a vertical stretch or compression. So in this case, it's a vertical stretch because 8 is greater than 0. So it's a vertical stretch of 8. I also see this negative out in front of the function, which means it's going to be a reflection over what? Is it over the x-axis or the y-axis? Well, it's out in front of the whole function, so it's a reflection over the x-axis. And this part of the graph here with the minus 7 means the whole graph is being shifted down 7. So where's the vertex going to be? Well, if our parent function was this parabola looking like this, we have vertically stretched it, which is going to make it look quite a bit narrower, like this, vertically stretched. It's been reflected over the x-axis, which means it's now very narrow, but it's opening this way, and it's been shifted down 7. So this whole graph is being shifted down 7. So I'm predicting that our vertex will be at 0, negative 7. Okay, and you could type that into your calculator and check me on that. All right, let's take a look at this example. This time we have the negative inside with the x, and the x is being multiplied by 4 also. Again, I see 3 transformations here. The negative inside the parentheses, which means that x is going to be made negative before we square, that is a reflection, this time over the y-axis. The 4 is also on the inside. That's being multiplied by the x before we square, so that's a horizontal stretch or compression. In this case, I have to take the reciprocal, right? So it's a horizontal something of 1/4, and since that is less than 1, that means it was a horizontal compression of 1/4. And then lastly, with the plus 9 outside, this is going to be a shift up 9. So where's the vertex for this? Again, what's going on? Our parent function, let's say, looks like this, but we have a horizontal compression. So that means we're pushing this graph in towards the y-axis. So the new graph is going to look narrower because it's being horizontally squished. And it's been reflected over the y-axis. Well, that's interesting. If I'm going to reflect this over the y-axis, then what's going to really happen? I'm going to flip this, flip it left, right. Well, guess what? You just saw me do it. I reflected over the y-axis, and it has not changed. And it's been shifted up 9. So we're up here somewhere. So I think for this one, the vertex would be at 0, 9. Okay, so let's talk about standard form. In your textbook, they refer to standard form as this form, f of x equaling a times x minus h quantity squared plus k. I will call it standard form like they do, but I really would also refer to it as vertex form. Because if it's in this form, you can see what the vertex is. You can just pick out what the vertex is. All right? So the form is f of x equaling ax squared, a times the quantity, x minus h squared plus k. This is your standard, also known as vertex form. All right? The axis of symmetry is going to be x equals h, and the vertex is going to be hk. If a is greater than 0, the graph still opens up. If a is less than 0, the graph still opens down. That a value is the same, and in both this form and the general form that we talked about. So let's take a quick example. Let's say we have f of x equaling 3 times x minus 2 quantity squared plus 4. The axis of symmetry is going to be x equals 2, right? Because x equals h is the axis. And remember, when you're writing the axis of symmetry, you have to put the x equals, all right, because you're talking about the line. You're giving an equation of the line. And the vertex is going to be the hk. So in this case, it would be 2, 4. This is your h. This is your k, right? H, K. Let's look at one more example of that. For this example, let's say we had f of x equaling 1/3 times x plus 5 1 squared minus 6. So in this case, the axis of symmetry is going to be x equals, is it going to be x equals 5 or x equals negative 5? Well, remember, the formula is x minus h. So what's being subtracted from the x is really a negative 5 to get me an x plus 5. So the axis of symmetry should be x equals negative 5. I like to just say, what do I need to, if I set this parentheses equals 0, what would I get when I solve for x? Well, I get negative 5. And that means that the vertex is negative 5, negative 6. Okay, so to graph a parabola, you would begin by writing the quadratic function in this standard, also known as vertex form, using the process of completing the square. Now, you remember how to complete the square, I hope, from our work in the appendix. We learned how to do it then. So just a quick recap, a review of what that means. First of all, perfect square trinomials, if you remember those. A perfect square trinomial is a special trinomial that can be rewritten as a binomial squared. So in this case, x squared plus 16x plus 64 could be rewritten x plus 8. X squared minus 8x plus 16 could be rewritten, could be rewritten as x plus 8 quantity squared. If I have x squared minus 8x plus 16, that could be rewritten as x minus 4 quantity squared. If you wanted to test it, you could multiply out x minus 4 times x minus 4, and you'll end up getting back to this. So the process, remember, is you take half of this number here, the coefficient on the x, and then you square it to get this number here. That's what makes a perfect square trinomial, and then this number right here is the number that goes in with the x. So in this next example, so x squared plus 10x plus 25 would be equal to x plus 5 quantity squared. X squared plus 14x plus what is going to give me a perfect square? Take half of the 14, that's 7, square it, and you get 49. This number 7 is what goes in right here with the x. So it could be rewritten as x plus 7 quantity squared. All right, one last example. If we had x squared minus 20x, what would we have to add to make a perfect square trinomial? Well, we would take half of the negative 20, which is negative 10, and then square that, which would get us 100. But it's this number right here that's going to go in with the x. So it's going to be x minus 10 quantity squared. All right. Let's go on. So let's practice. We're going to put this equation into standard form by completing the square. Is it in standard form? I'm sorry, is it a perfect square trinomial right now? Well, if I took half of negative 6, I'd get negative 3. Is negative 3 squared equal to 4? No. That means this 4 is messing things up. So I think our first step is going to be to slide that 4 out of there, but leave some room to complete the square. So we would want to take half of negative 6, which is negative 3, and square it, which is 9. But I can't just add 9 to one side of the equation, then now my equation's out of balance. So what we want to do is we want to subtract 9 from this function. But wait, make sure that you only have a 1 as the factor out in front of your parentheses, because you really have to multiply the 9 times that number, and then that's what you really added to the function. So we really added 9, so we're going to subtract 9. So now to put this into standard form, we're going to write y equals 1 times x minus 3 quantity squared minus 5. That is your equation in standard, aka vertex form. Let's take a look at another example. What about this one? So do we take half of 24 and square it? No, because this coefficient is not a 1. So be careful. We got to factor out that 3 first. But remember, this negative 5 is not part of this deal, so it has to stay out of the factoring part. So we're just factoring out a 3. So we'll have 3 times x squared plus 8x. I'm leaving some room to complete the square. I'm closing my parentheses, and then I'm putting this minus 5 over here. Okay? So again, the process of completing the square, we're going to take half of 8, which is 4. Square that, that gives me 16. But I just changed the right side of the equation by putting a plus 16 in this parentheses. So you may be thinking, oh, subtract 16. But no, you don't want to do that, because by adding 16 right here, this 16 is inside this parentheses, where everything is going to be getting multiplied by the 3. So what I really added to this function was 3 times 16, which is 48. So what I want to add here, or I should say, what I want to do to counteract adding 48 is subtracting 48 here. So what's our equation in standard form? Remember, standard form is y equals a times x minus h quantity squared plus k. So in this case, we're going to have y equals, here's my a, right here's the 3. This can be rewritten in binomial squared form, so that's going to be x plus 4 quantity squared. And then minus 5 minus 48 is going to be a minus 53. So that's going to be my equation in standard form. Once you see this, you could identify the axis of symmetry. That's going to be x equals, remember this is like x minus h here, so the h must be negative 4. And the vertex would be negative 4 comma negative 53. Let's take a look at one more example of this type. Again, the directions we would want to put this into standard, aka vertex form, by completing the square. So we are going to factor out, we can't do any completing the square with this negative 2 here, so we're going to factor out a negative 2, but just from these first 2 terms. This plus 12, staying out of it, that goes out here. So if I factor out a negative 2, I'm going to have x squared and negative 2 times a positive 5x. Negative 2 times 5x would get me to the negative 10x. And I'm leaving some room to complete the square, because now I have a leading coefficient of 1 with the x squared. So I'm going to take half of the 5, which is 5 halves, and then I'm going to square that, and that's going to give me 25 fourths. Because 5 squared is 25, 2 squared is 4. But I can't just leave it like that. I just added something to the function, and I've altered the right side of this equation. So what I'm going to do is figure out what I'm going to have to add or subtract over here to counteract this. Well, what did I really add to the function? I really added, remember, this negative 2 is getting multiplied by everything in the parentheses. So I really added a negative 2 times 25 fourths, which would be, let's see, 2 goes into 2 once, into 4 twice. That's really negative 25 halves that I added to the function. So to counteract that, I'm going to have to add a positive 25 halves out here. All right, so overall, we got this ready to write in standard, aka vertex form. So it's going to be y equals negative 2 times x plus, remember, here's our number that goes in with the x. So it's going to be x plus 5 over 2, quantity squared, and then plus, what's 12 plus 25 over 2? Well, the 12 is 24 halves plus 25 halves. That sounds to me like it's going to be plus a 49 halves. So this is our equation in standard form, vertex form, and our vertex is going to be negative 5 halves, comma, 49 halves. All right, so I'm going to skip that example. Let's take a look at this. Write the standard form of the equation of the parabola whose vertex is negative 4, 11, and that passes through passes through negative 6, 15. So you're trying to write the standard form. Standard form, as you know, is y equals, or I'll write it as f of x equals a times x minus h quantity squared plus k. So we want the equation of the parabola where the vertex is negative 4, 11. Well, negative 4 goes in for h, 11 goes in for k. So far my function looks like a times x minus a negative 4 is going to be a plus 4, quantity squared plus 11. That's my equation, but I can't just leave it there. I need to find the value for this a. And so in this case, I'm going to plug in negative 6 for x and 15 for y.
Sorry, I'm just checking.
That's okay. And so I'm going to plug in negative 6 for x and 15 for y so I can solve for a. And so I got 15 equals a times negative 6 plus 4 quantity squared plus 11. And so now we're just going to solve this equation for a. So negative 6 plus 4 is going to be a negative 2. So I've got a times negative 2 squared plus 11 equaling 15. Negative 2 quantity squared is a positive 4. So I get 4a plus 11 equals 15. I'm going to subtract 11 from both sides. So I get 4 equals 4a. And I divide by 4. And it turns out that a, for this example, is equal to 4.
Sebastian Tovar, please come to the office. Sebastian.
So when we
Tovar,
write
to
this
the office,
function
please.
now, all we need to do is plug in that a value that we just found right here in this model. So our answer is going to be f of x equaling 1 times x plus 4 quantity squared plus 11. And what's the vertex going to be? Vertex, well, we already knew that. That was given to us, negative 4, 11, right? Yep, vertex negative 4, 11. Let's try one more of these. Write the standard form of the equation of the parabola whose vertex is 5, negative 2, and passes through negative 1, 4. So again, we want standard form, which is y equals a times x minus h quantity squared plus k. We're going to plug in the 5 for the h and the negative 2 for the k because you're told that that's the vertex. So 5 is going to go in right here. Negative 2 is going to go in right here. So I'm going to write y equals a times x minus 5 quantity squared minus 2. That's our equation, except we still need to find this a value. How do we find the a? We plug in the -1 for x and the 4 for the y. So I'm going to have 4 equaling a times -1 minus 5, quantity squared, minus 2. And I need to solve this equation for a. So -1 minus 5 is -6, and I need to square that and then multiply that by a, and then subtract 2 from that, and that's going to equal 4. That's going to give me a positive 36a minus 2 equaling 4. Add 2 to both sides, and you get 6 equals 36a, and divide both sides by 36, and I'm getting a to equal 1/6. So in this case, my answer for this vertex form should be f of x equaling 1/6 times x minus 5 quantity squared minus 2. All right. So just a little recapping here, a parabola that opens up. If a parabola opens up, is it going to have a maximum value or a minimum value? Well, it's going to have a minimum value, right? Because there's going to be a lowest point. There is no highest point because it keeps going up higher and higher and higher. So it has a minimum value. And if you've got a parabola that's opening down, it's going to have a maximum value. The maximum or minimum value is the y-coordinate of the vertex. All right, so to find the vertex of f of x equaling, let me fix this up a little bit. To find the vertex of f of x equaling ax squared plus bx plus c, you could use the formula x equals negative b over 2a. This really means the x coordinate of the vertex is equal to negative b over 2a. Very handy formula in case your function is in, I'll call this general form as opposed to standard form. All right, and then once you find the x coordinate, you could plug it in to find the y coordinate of your vertex. All right, so let's try this example out here with this problem. The height y in feet of a ball thrown by a child is given by y equals -1/8 x squared plus x plus 4, where x is the horizontal distance in feet from where the ball is thrown. So how high is the ball when it reaches its maximum height? Okay, so if you're picturing what's going on, we have a ball that's thrown by a child and the path of the ball is looking something like this. How do I know it's opening down? Because I can see my leading coefficient is -1/8. So I want to know what is this highest point. Well, what do we call that highest point? We call that the vertex. So to find the vertex, since this equation is in general form, right, we're going to use the formula that the x-coordinate of the vertex is equal to negative b over 2a. So in this case, if we're doing negative b over 2a, we're going to take opposite of my b value. Remember, a is -1/8. As we look at this, b is the coefficient on x, which is just 1, and c is 4. So I want opposite of b, so I want opposite of 1 over 2 times my a, so that's 2 times -1/8. Opposite of 1 is -1. 2 times -1/8 would be a -1/4. And if I'm dividing by a fraction, I can multiply by the reciprocal. So I can multiply -1 by -4/1, and I get 4. What did we just find out? We just found out that the x-coordinate of this vertex is 4. So that means right here on my x-axis, we've got to go 4 units over to get to that highest point. And to find that height, we're going to plug in 4 wherever we see an x in the function. So I'm going to plug in 4 here, and I'm going to plug in 4 here. So I'm going to have y equaling -1/8 times 4 squared plus 4 plus 4. And so when I do that, I end up getting what? Negative 1/8 times 16 plus 4 plus 4, that's really plus 8. And so negative 1/8 times 16 is negative 8, and negative 8, I'm sorry, negative 1/8 times 16 is a negative 2, plus 8 is equal to 6. So that means our y-coordinate should be 6 at the vertex. So the maximum value of this vertex is 6, not 4, 6, but just 6. And so the maximum height that this ball reaches is 6 feet. All right, so it gets up to 6 feet in the air. All right, that completes this video. Thanks for watching.